Let y equal f of x be a solution to the differential equation x dy plus y minus x e to the x dx equals 0, such that y equals 0 when x equals 1. What is the value of f of 2? I'm not sure what my first instinct here is exactly. I guess we're going to want to integrate something between the values x equals 1 and x equals 2. Right, let's do it. Let's write out what we're given. And write out what we're given and just like manipulate this differential equation to give us something that we want. Like, if I rearrange this, you know, I get this is exactly the quantity we want. We want y when x is equal to 2. This is given as being 0. This is a problem though. So how do we get rid of that? I feel like unfortunately now I've sort of solidified this approach in my head as the way of doing it. It's going to be hard to undo my first approach here in my mind. Okay, let me think. I think this will lead us there. So I recognize that, you know, I have an x dy. If I expand this, I have a y dx. That sounds like product rule to me. So by rearranging things to make it look like a product rule, I have the derivative of the product is equal to x e to the x. So the left-hand side is x f of x evaluated at the endpoints 1 and 2. On the right-hand side, this we may have to do an integration by parts. Okay. So here I have 2 times f of 2 minus 1 times f of 1 on the left. On the right here, I've got 2 e squared minus e minus the integral of e to the x from 1 to 2. This is going to be e squared minus e. We're given that f of 1 is equal to 0. So I have e squared, 1 e squared cancels, and that e cancels there. So I just have f of 2 is equal to e squared over 2. Yeah, this was a cool problem. Honestly, it helps to be comfortable with a lot of these informal manipulations of differentials and so on, and just really understanding that, you know, understanding in which ways it is appropriate to manipulate an expression involving differentials. This is one of the options, right? Yes, option C is e squared over 2. Yeah, like a lot of what I did here is clearly very non-rigorous, but I suppose it could all be made rigorous if we had to. Yeah, but a very, very computational problem if you're comfortable with these types of differential manipulations. If I have more to say about this, I'll put it down in the description. Thanks for watching.